It is my pleasure today to welcome Carla Gonçalves to this DaSSWeb series. Carla is a mathematician. She did BSc, Bachelor Degree in Mathematics, as well as MSc and PhD in Applied Mathematics here at the University of Porto. Currently, she is researching forecasting methods and data sharing incentives at INESCTEC. She is also an invited professor at FIOP. Carla, thank you very much for accepting our invitation, and the floor is yours.
Thank you for the invitation and thank you for the introduction. So I will share the slides. Let me just maybe okay, can you see the slides full screen?
Yes, that's fine.
Okay.
Thank you.
Perfect. So good afternoon all. So as Professor Maria Eduarda said, my academic background is in applied mathematics, and during the last few years I have been working in renewable energy forecasting, and I have recently focused more on collaborative forecasting models and incentives to promote such collaborative forecasting. And that's why this presentation is about designing incentives for collaborative forecasting. So first of all, the context. Why do we need collaboration? Why do we need incentives? So we live in a modern society where much data are being generated and collected, and this includes in power systems where we have many sensors collecting meteorological features, power consumption, power production, charger, electrical vehicles, chargers, occupancy, and many other features. And there are also many studies showing that if we combine different data sources, we can potentially improve our forecasting models. And to give you two examples in wind power forecasts, if we have multiple wind farms and and the wind tends to move from the left to the right, then the wind farms on the right would benefit if their model was fed with data from the left wind farms. So the right wind farms could use data from the left wind farms and use them as a sensor to capture, okay, the wind forecasts say I will not have wind, but they are having huge production, so maybe I will also have, so I should correct my forecasts. This is an example. Another use case is if we have multiple independent forecasters who train their models to predict the same target variable, then an ensemble of these forecasts tends to be more accurate than each forecast individually. And this collaboration seems perfect. It's not a new discovery. In fact, we have this paper with more than 10 years. So more than 10 years ago, we already concluded that collaboration can be helpful to improve forecast accuracy. It seems perfect in a scenario where everything is open data, open code, open science, but although there are many open source initiatives, there are also many closed data use cases. There are many companies that, due to privacy or intellectual property or regulatory reasons, are not able to share their data. And these closed data sources, let's say, are our focus. And how can we create incentives for data sharing in such proprietary data cases? So first, we can design approaches to allow data owners to collaborate without sharing sensible data. So we can train models, ensuring data privacy, and we have better forecasts. So a classical way to do so is by adding random noise to the sensible data. This technique is called differential privacy when the noise has certain properties, statistical properties. Usually the Laplacian noise is the one that guarantees, that has more guarantees. We also can have the Gaussian noise. The problem with this technique, it is a very simple technique. It's independent of the model we use. But the problem with this technique is that there is a trade-off between data privacy and data utility, because the more noise you add to your data, the more protected it is, but the less information it provides to the collaborative models. And another way to do this without hurting the performance of the forecasting model is by using encryption techniques. And in 2020, we proposed the privacy-preserving model to use spatial temporal data without the risk of disclosing private information. So we assume different power producers have their historical time series, and then they use a vector autoregressive model to predict the next few hours. So it is a simple approach where the next values for all locations are a linear combination of the most recent power measurements in all the locations. The problem is that we have to trade data to find cross coefficients, so these ones here. And since our model is linear, our solution consisted of encrypting sensible data with linear algebra in such a way that the original linear system is transformed into an equivalent linear system. And in this way, agents share an equivalent version of their sensible data. They can solve the problem in a distributed way and recover the solution of the original problem at the end. And this is an example of what we see in the literature as vertical federated learning. So federated learning, because we can distribute the problem across the agents, and vertical because when we organize the target matrix and the input, the covariate matrix, we see that data is vertically split among the data owners. And although it is relevant to advance with these type of approaches, privacy-preserving forecasting, collaborative forecasting, and we are doing that in our team, this might not be enough to promote data sharing. For instance, in my initial example with wind farms in the European map, the wind turbines on the right will be very happy with the results of the collaborative forecasting models. But in the scenario that I described, these ones, the left ones, will just help the right ones to improve their models, but they have no benefit with that. So why should the left wind turbines help these ones if they are not having any benefit with that? And we answered that they could help their competitors if they receive some compensation. For example, a monetary compensation. And this is how we ended up designing data markets for multiple use cases. I'm not sure if, okay, let me just move, okay. So in the next slides, I will briefly present some of our algorithms. Our focus is on forecasting use cases, which means that the motivation to enter the data market can be to improve the forecasts with data from the others, or share data to receive some compensation. And here we identify three possible groups of incentives. In our first group, we consider that there are agents that want to sell data and agents that want to buy forecasts produced using this data from data sellers. For example, buyers can be wind farm operators who want to predict power production for the next hours, and sellers are weather forecasting companies. Sellers can also be wind farmers, because a wind farmer can buy forecasts and also sell his own data. The second group considers a scenario where data owners have their covariates and target variables, and they enter the market to exchange data with others. But in this case, the exchange, so I will receive and share data with approximately the same value. For example, wind farmers can share weather forecasts for their locations if they receive weather forecasts from other locations, and the shared value and the received value is approximately the same. Here, the challenge is how to measure the value. And finally, the third group is about sharing data to receive some service or some recognition. And an example, so we share data with Google, and we are fine with that, more or less, because we have many free services like the Google Maps. And this is an example of a data by service. So we share data to receive a service. Another possibility is sharing data because I'm helping to design the carbonized world, and I will be recognized by the society or the community because I'm doing that. When I share data for free, let's say, this is called data altruism. So I'm able to share my data because I believe it is helpful to some model or to help mitigating the climate change. And that's it. So today I will focus on the first two groups, but data altruism and recognition can be easily integrated into the solutions that I will discuss. Okay, so So regarding data monetization, we have some solutions, but here I will describe one of them. One of the simplest strategies that we have. And here we have agents with their local covariates, the X, and the target Y, and they enter the market to buy forecasts with a certain budget P. So there are agents that enter the market, data owners, they enter to buy forecasts, and they have a certain fixed budget P, capital P. And their rationale is, I am able to pay up to P for a prediction better than mine, because he already has a local feature, he has a target, so he can construct a model, and he wants to acquire data from the others only if it improves if the prediction is better than the one that he already has with local data. And this budget P can be a budget per timestamp, for example. For each timestamp, he is able to pay up to P. We also have the data sellers, whose rationale is if my variable x1 is used to generate forecasts, then I want to receive this value P1. And this value should reflect at least the cost of sharing the data. So the infrastructure to collect the data and share it with this structure, the platform, the data market platform. And to orchestrate the process, so we have the data buyer, we have the data sellers, and we need some entity to orchestrate the process and ensure data privacy. And this entity is the market operator. So we have the market operator that receives all data and bids and generate the best forecast possible given the restrictions. So in the simplest design, we can assume a linear collaborative model. So the target is simply a linear regression model that has to be estimated taking into account that the sum of the prices for the variables allocated should not surpass the buyer budget. So this is a simple cost-constrained linear regression, and it can be solved as a sequence of DaSSWeb problems as proposed in this paper from 2022. So it's an efficient solver for this problem. Now, the problem with renewable energy forecasting is that for horizons, so for very short-term forecast, we can simply combine the most recent wind power measurement, and the linear model is a reasonable model. So we have the right assumptions because the relation is still linear up to 6 hours. But after that, we need also to consider the weather forecasts, and the relation between the weather forecasts and the power production is non-linear. So this model is not a good idea. So our idea to deal with that is to extend the method to incorporate spline transformation. So instead of considering the features, for instance, the wind speed forecast, we consider transformations of the wind speed, like wind speed power 2, wind speed power 3. There are other families of splines, much more complex, just an example. And at the end, we still have a linear model. We need to transform features, use Bayesian optimization to find the best transformation. But at the end, we can still have a linear model and use the same solver to find the best spline regression, subject to the restricted by the cost of the model. Something we also consider here in the constraints is the fact that if agent one wants to receive 5 cents for the variable x1, so if variable x1 is used here, he asks to receive the 5 cents. But then the market operator does the transformation. So all these, let's say, variable x1 can result in 10 new variables. How can we capture that in the price constraint? What we consider is that if at least one of the new transformations of x1 is used, then the agent should receive the P1 he asked for. So if two are used, two transformations of x1 are used, he will still receive just P1 because he did not provide the transformations. He just provided the feature and said, I want to receive P1 if it is used. Okay, so we adapted the solution here to solve this problem. So it's also a sequence of DaSSWeb problems. And then we introduced one more improvement, which is maybe the buyer budget should depend on the accuracy improvement, because if he has the local model, he has the collaborative forecasting model, if the improvement is 5%, he will probably have a budget. If the improvement is 30%, he will probably have a higher budget. So what we did was we introduced a buyer bid that is based on the accuracy improvement. So instead of sending a fixed value, the buyer will send a function that says how much he wants to receive. Here, for example, the green is the value function of this buyer, and what he is saying is, if I pay 10, then my improvement in the root mean square error should be at least 90%. If I pay 30, then the root mean square error improvement should be at least 42. And then we solve the DaSSWeb problems for all these possible bids, and we select the bid. So the final payment will be the bid where the gain was maximum inside this acceptable region. So this is our proposal. We are right now waiting for a review. The paper was submitted for this journal. Now, in terms of validation, we start with a synthetic case study where the data buyer has 10 features. And there are 90 features available in the market. They all cost 10 cents, except the variable 37 that costs 11 cents. And we know that, so the target depends on these two features came from the buyer. And these ones are the ones that he should buy. And then we simulate different things like we assume that X3 and X73 are similar. And here the idea is to see if the model is able to capture that X3 is already owned by the data buyer. And then the market should not select this one. We also consider that X37 is similar to X74, so two features similar. This one is more expensive. They all cost 10 except this one that enters here in the model that generated the data, but this one is the cheapest option. So the model should select this one instead of this one because they are really similar, but this one is cheapest. We then simulated the market. We have to fix the bid for the buyer. We considered two cases. The case one is the buyer bid is 50, but each feature costs 10. Meaning that if we have 8 relevant features from the others in the market, the optimal model costs 80. This means that if he bids 50, there is no enough budget to buy all the relevant features. So with that, we want to check if given a restricted budget, if the model is able to capture the 5 most valuable features. And we see, so here is the optimal feature selection. So it should first select the variable 21, 90, 633, and so on. And here is the relevance estimated with permutation importance in the real model. And here is what happened when this model, when data is generated with a linear model. We see that the market was able to select correctly the 5 most relevant features, and it was able to, between 37 and 74, it selected the 74. So it seems to work well for this case. For the nonlinear case, we assume an exponential, so we have a linear sum, and then we apply an exponential to distort a bit the relation, and we see that still in that case, it is able to select the 5 most relevant features. In case 2, we assume that the buyer budget is 100. So 100 is enough to buy the 8 relevant features plus 2 non-relevant. And our idea is to check what happens in this case. And we see that for the linear case, it works well. So it just selected exactly the 8 features that it should select. For the case 2, it failed to select this variable 31 in the nonlinear case. So we have lowest importance, and it was not able to capture this feature. But at least it didn't select wrong features. So the buyer did not pay for irrelevant data. Okay, we also applied this algorithm to wind power data. Here we have almost 2 years of historical data for 10 wind farms located in Australia. It's hourly data. The goal is to predict the next 24 hours using wind forecasts. We have the wind for like U and V components. It's like we represent the wind speed and direction in the Cartesian plan. And we have these forecasts for 2 different heights, so 10 meters and 100 meters above the ground level. And here in this slide, what we do is we are assuming that using spline regression is a good way to capture nonlinear behavior, the nonlinear relations between wind speed, wind components, and wind power. And what we do here is we compare. So LASSO is simply a linear model, and we see that solid lines is the performance in terms of root mean square error. The performance when we consider, so we estimate zone 1 using data from the 10 zones, and dashed line is modeling zone 1 using only data from zone 1. So in general, we see that dashed lines are a bit worse than solid lines. So collaboration tends to help the forecasting models. although the extent of this improvement significantly varies across the zones. And this is a validation that we really need data markets, because if the improvement is different between zones, we need to create incentives for them to share data. So the lasso is simply a linear regression. We see that it performs much worse. It's not a surprise. We then have the spline lasso that we use in our data market in blue. KR is a kernelized regression, a nonlinear model, and the gradient boosting regression trees are the GBRT. And we see that in general, although the spline is a bit worse, it's not. It has a good trade-off between execution time and performance. So we are happy with the selection of the spline regression to represent the relation between wind forecasts and power forecasts. Now, in terms of the market, we simulated the data market with different bid functions that we can see here. The first bid function assumes that data buyers are able to pay 36. The second value function is only 10. And then we have these variations like linear relation between the value is able to pay and the error improvement, and something more like that. So he has a huge valorization in the beginning, but then it stabilizes around the 30%. And overall, the conclusion is that higher buyer budgets lead to better performance because they can acquire more relevant data, and data owners improve accuracy and or receive monetary compensation. So in some cases, they don't have huge improvements, but they receive money from the others because they are helping the others to improve their forecasts. In other case, they don't receive that much money from the others, but they have big improvements in their forecast accuracy. So overall, all these 10 zones have a motivation to stay in this data market. Okay, so just to conclude this part of data monetization, of course, this is a spline regression where we transform each feature individually. But there are cases where probably it would be more useful to consider like interaction between features, mixed effects like products between lags. And in fact, there is this paper that it is a recent paper that states that, and they show with many experiments, that a linear combination of mixed effects between shifted time series can serve as a powerful model and capture efficiently the dynamic system data through observed time series. In our case, we could adapt, or this would be future work, we could adapt these knapsack problems to take into account also the interaction between different lags. But in that case, we would have a quadratic knapsack problem. So this would be the next step. And future work would be also to extend this to classification problems. For instance, wind turbines, wind farmers could exchange data of their operational features to detect if some wind turbine will fail, for example, because they have huge costs with that. Okay, now moving to data by data. Let me see the time. Okay, now moving to the data by data, just to give you a brief idea of what we are doing. So here the aim is to encourage data exchange with data of similar value. The goal is to maximize the total value exchange, restricted by the fact that shared and received values should be similar. So mathematically, we can represent it like that. So we want to maximize the overall sum of the value of the J line feature from the J agent to when it is shared with the I. This is the feature that we have to optimize. It will be a 0 or 1, allocate or not this value. And then we have the restrictions to ensure fair exchange. And we also need to have restrictions to capture redundancy between features, because if we know we can have two relevant features, but they are strongly correlated, then if we select one of them, we should not select the other one. But at the end, if we look to this problem, we can rewrite this condition as two conditions, and we end up with a linear problem that can be easily solved with a Python package like SciPy or something similar. So a big question is, what is the metric, the best metric, or to find this value of the data? And we did some synthetic case studies. This is one of them. So we basically have 5 data owners. We assume that, for example, data owner 1 has a target variable that depends on own features and also on features from agent 2 and agent 3. The same for agent 2. So agent 2 is a target that depends on own features and also features from agent 1 and agent 5 and so on. This is the way the target for each of them depends on the others. So here is the weights for own data. So they depend on their own 3rd and 7th features, and then they depend on the features from the other 2 in this way. Each of these agents have 30 covariates. So in the market, when agent 1 enters the market, he has 30 covariates, and there are available 120 from the remaining 4 agents. So we try to evaluate first what is the best metric to detect if a feature is relevant or not. So we compare the classical correlation methods, Pearson, Spearman, and Kendall. We then have mutual information, phi-k. Phi-k is a recent metric from 2022, I think, and then distance correlation. So these ones are the non-conditional ones, and then we also have to consider conditional metrics, because the reality is that we need to take into account that the data already owns data, and that there are relations between features, and if I acquire one and the other is already captured, then the added value is 0. So we use the permutation hypothesis test for each of these metrics. So we have the metric, we do the permutation, a huge number of permutations, and we can have a p-value. And then if this p-value is below the 5% significance level, we consider that this feature is relevant and should be and could be traded in the market. So here we are just seeing the results for relevant or not. To measure the performance of this classifier, we use the recall metric and precision. So we want that recall is important. We want it close to 100%, because recall is related to given the relevant features, how many of them I was able to detect. And it is important that I do not discard relevant features. So we want a recall of 100% or close to it, but we also need to take into account that an easy way to have a recall of 100% is classify all features as relevant. But then we are not taking a good conclusion, because we also want to reduce the search space of our algorithm, and then we should also consider precision. Here are the results. As I said, these first metrics are for non-conditional relation between the features in the market and the target of the 5 agents. In general, we see that for linear and exponential relations, these metrics achieve a good recall, a reasonable precision. The computation time is also okay. But when we go to quadratic relation, and we are not considering interactions, the Pearson, Spearman, and Kendall start failing. Although mutual information, FIK, and DCOR still have a good performance. Regarding the conditional metrics, and here conditional to data owned by the agent that is trading. So if I am trading data, I want to acquire data that is correlated again to my target, but it should be very different from the features that I already have to explain my target variable. Otherwise, I'm not having a value addition. Here, again, metrics based on on Pearson and Spearman, like partial Pearson, and partial Spearman, or mutual maximum relevance, minimum redundance. They have poor performance, but we see that conditional mutual information is able to capture almost all the relevant features with a good precision as well, and reasonable computation time. To conclude, there are metrics like these ones. They have good performance, but then computation time is a bit exaggerated. And if we have a data market with hundreds of agents and we have to update it every hour because it happens in power systems problems, we need to generate new forecasts every hour. So if we have to rerun this every hour, it is important to have a fast solution. And it seems that the maximum relevance, minimum redundance, based on mutual information has the best trade-off between these three criteria: recall, precision, and time. So based on that, here we just see the metrics that are good to detect is relevant or not. But now, what is the relation with data value? Because the goal of the market is trade data value. We did some plots where we compare the metric value. Here we have the maximum relevance, minimum redundance for mutual information, for the distance correlation, and for the FIK metric. And in the y-axis, we have the permutation importance of the real model because we generated the data. We know exactly the coefficients of each feature. So we can permutate the feature and see the impact in the output and measure the permutation importance in this way. And we see that, in fact, for mutual information, the relation between metric value and the variation in root mean square error, we see a clear relation. For the distance correlation, we also see. But for the FIK, we have high dispersion of points, so it suggests that, in fact, FIK is not a good idea between mutual information and distance correlation. Mutual information is faster, so it's our choice. To finish the synthetic case study, so the goal is to trade features between these 5 agents. So we simulated the market, assuming that the value, this V, is measured then with MR, ME. And we saw that in general, data owners exchanged, it was supposed to exchange 10 features each. They, for example, owner 1 exchanged 11, 9 correct, 2 incorrect, owner 2 these. So in general, they still exchange some wrong features. This is what we see in the precision, because there are still features that are classified as relevant that are not really relevant. They are close to, but they survive the filter, and they are still being exchanged. And this is also related to the threshold that we impose. When we optimize, we have this restriction of the shared minus received smaller than a threshold. And depending on the threshold, this also changes, of course. Okay, regarding the wind power data set that I described before, from the 10 zones, 10 wind farms located in Australia, here what we see is if zone 1 used a local model for the entire testing period of 1 year, then it would have this root mean square error. If this zone used the collaborative forecasting model without restrictions, so combine all the data, this would be the root mean square error. And when we force this thing of let's trade weather forecasts, but the shared value should be equal to the received, we see a value between the local model and the collaborative, the perfect collaborative model, and it makes sense because we are restricting some connections. Okay, and let me see. Yeah. Okay, so I will stop here. So I think it was already a summary of the different initiatives we have. The key message is collaborative forecasting has potential to improve forecasting accuracy in many use cases. Here I focus in energy because I'm part of the Center for Power and Energy Systems, but there are other use cases in logistics, in health, many other use cases. Data sharing incentives are needed to promote such collaboration because we have many open data source initiatives, but the reality is that there are still many companies that are not able to share their data, and their data is important to improve the performance of many models. Here we are exploring incentives, different types of incentives. Our focus is on essentially data monetization and now also barter trading with data by data. And during these last years, it all started with this European project, Smart for Hash. After that, we moved to two new European projects, the EnerShare and Green Data AI. And more recently, we were contacted by a company that is interested in this platform, the Elia Group. Elia is the transmission system operator from Belgium. So they are interested in using our algorithms to predict offshore wind power. So offshore is wind turbines in the sea. And okay, and although all this is designed for proprietary data, I would like to emphasize that all our developments are open source. Our codes are open source, and you can find them at InEschTech GitHub. And just to conclude, this is the team that works with me. So these two on top, José Andrade and André Garcia, they are from informatics. They are taking the algorithms and doing a prototype because people will not run the Python scripts I do. They need like fancy APIs with buttons and things. A prettier representation of that. So these two are responsible for that. Then with me in the algorithms, I have Giovanni Buroni, Fernando Paula, and the supervision of Ricardo Bessa, because this is a multidisciplinary problem. And we are all from very different backgrounds, but yeah, that's it. Thank you.
Okay, Carla, thank you very much. It was very, I think, enlightening and very interesting. And you know that I find this really interesting, a challenge and very, yeah. So anyone would like to ask some questions? Any question?